Right? So let me welcome Zhi-Yang, our speaker for this track. So Dan is actually he's my ex-colleague from Shopee, but now he's in Shopify. Okay. Okay. And anyone uses database here, right, at work, right? So he'll be talking something about database, which I don't really know a lot of. So probably I'll try to learn something from him, because I'm a front-end engineer. I don't really know about database. So let's welcome Ben on storage and retrieval in databases from scratch. Floor is yours.
Thank you. I wasn't nervous until I actually have to start speaking. So hopefully this will go well. Okay. So this talk, how it came about and why did I choose such a complicated book to talk about? So as you all know from the introduction, I was his colleague. So naturally, I'm also a front-end engineer. I started working full stack maybe only about a year ago, and I'm still learning on the job. So there were a few of us that converted from front-end to full stack. So one of the things we had was we decided let's actually get good at doing full stack, and we have a book budget. So we decided to let's randomly choose a book on back end, and then make sure that everyone reads it. So randomly chose this designing data intensive applications. I've been told that this is the Bible for data engineering. I didn't know that when I read it. Yeah, and the format was that we would present a different person would present one chapter every week. So I stupidly decided to volunteer to present twice. And when I finished the slides for this one, I was so proud I had to share this with other people. That's why I'm here for this talk. Yeah, so designing data intensive application is a good book, but I don't recommend reading it because it's very, very, unless you know what you're doing. So I'm trying to simplify a little bit of what I learned, specifically from chapter 3, because that's up to where I understood things. From then on, it went downhill. Yeah, it's rough, man. So as Li-Hao has introduced, my name is Zhi-Yang. You can call me Ten or Tenzi. If you want to get the slides, you want to get the code examples, they are all, you can just search TZYINC on slides.com and CodePen respectively for slides and code. Yeah, so software developer at Shopify, not the other one. And I like to write a lot of nonsense in HTML, CSS, and JS. Sometimes, like this CSS poop that I'm very proud of, and yeah, other things. So that's the link for the slides and the code pen. So first is let's define database for the purpose of this talk, right? This talk, we won't go any deeper into your joins, your complex commands. We will just want to do storage and retrieval. We're just storing data with a key value pair. So with the key, we store it with the key and the value, and given the key, we want to retrieve data. And we want to retrieve it in a somewhat efficient way. And there are two, yeah, so that's on the most fundamental level, right? That's what the database does. It just needs to store data, and when you ask it again later, it should give it back to you. And you can generally categorize database into two types. There might be more. I'm just following off the textbook. But there's online transaction processing, which deals in mostly your business logic, right? You want every transaction, whatever you do, you want it to be quick in writing and also quick in retrieving. Alternatively, you can have the online analytical processing, which is where you do your data engineering. You want to store large amounts of data, or you want it to be retrieved quickly because you want to do your analysis. You want to maybe manipulate how it's being given back to you. We'll focus more on OLTP today because that's what I understood. Okay, so first example that was given in this book, right, was that there's this world's simplest database, right? So essentially, what's the simplest way we can think to write into a file? It's just, I do need the mouse here. So what we have here is basically, I do need to look at the screen. This is complicated. No, I don't need a mouse. Okay, so over here, we have two commands. We have a dbset and dbget. The reason why I chose JavaScript is because I'm more familiar with it, not because it's good. I do love my JavaScript, but it's not good. So we have, essentially what I just do is I just get data from the browser, the local storage, and then that's for db get, right? I'm just getting the data from the local storage, and then for db set, I am getting the data and then writing the content with the new input, the new string. And then I will just update the display here. So if we put any key value pair, I believe it's a comma. And then it gets appended to the end. So in the actual example, there is no get where you get all the data and there's no like pulling all the data out to append and writing it in. You're just appending to a file. So what happens is that when you do this kind of things, the storage is pretty quick because you just append to a file. It's very cheap to do. Yeah, and here I just use poop emoji as a delimiter because I could. So some learnings that I did on this, like I said earlier, writing has pretty good performance, right? Because you can just append to the file. And this basic principle is so simple, right? It's just writing it to the file. And then when you need to retrieve it, you just iteratively comb through in a log n time linear search. It's considered a bit slow, but it's good enough. And it's so useful despite being so simple that it's still being used in logging subsystems in databases, at least the more simple. I mean, they have a lot of other features to retrieve, but this is still being used, right? Yeah, reading requires you to find the start of the next key, so that's why some form of escape is necessary. I use a poop emoji. You can use whatever thing you want. And when I first wrote this, I think I didn't realize that the poop emoji took more than one character, so the comparator was messed up with my storage. So that's one thing that if we want to rewrite this from scratch, we might want to think about. And writing to multiple files and reading requires some form of pointer to remember where you are and where to write. So when you want to append, you need that pointer to know where to append to. Yep. So next, some improvements that was mentioned in the book. You can do segmentation. So you want to write to multiple different files. So maybe you hit a certain size, you want to segment yourself to a different file, right? And then once the log becomes too long, there's too many files, you can do some form of compacting. So you want to squash things with the similar keys and values together. When you retrieve the store and value, it doesn't overwrite the previous value. It is still stored as a log, right? So, but but when you want to retrieve the key and value, you just want to retrieve the latest value, and that's good enough. So you go backwards to find it. So when you compact, what you do is you squash all the old keys together, and then you get basically a smaller file once you run out of this space. Yeah. So that's merging segments that you can do. So you can combine the segments together, or you can compact each segment itself. And crash recovery. I can't remember why I wrote this thing. So you can do some crash recovery. I guess when you do a refresh for the previous page, right? For this example, it's basically like a crash when you refresh the browser. Yeah. So basically you can have a checksum to see if when you are appending halfway through or any other transactions, you want to make sure that at least the values are still correct as what you remember. So that could be one of the improvements that we do. Okay, so for the next structure that we're going to talk about is hash indexes. So indexes are additional data structure. So on top of just appending things, you might want to have indexes for easier retrieval, quicker search. Right? Any kind of index will slow down your write because now you're doing extra work once you are doing an index. But it can greatly speed up your retrieval queries. Right? Since this is a trade-off, right? When you actually use a database, let's say you're a system admin or your application developer, you are usually given the choice to choose your indexes manually because you as a developer, you as the system admin knows best what is the best thing to index. So that's generally why the control is given to you. It's not something that should be done automatically, even though I guess some systems will. Yeah, so for this, in this example, the hashing algorithm is just to use the string itself. There is no hashing algorithm. It's just using the string. But what happens is that we have a in-memory hash, right? So this is in my memory, and to retrieve it is basically instant. And what you can notice is that the value is actually not the content itself, but is the address at where, in this case, the length of the string to my different to my record. Which one belongs to this which is the most common recently added thing. So if let's say I overwrite the hash of A, right, so it gets appended to the end and the hash gets updated. Yeah, so when I want to retrieve again, and then I get back the most recent value because it's from the hash. So this is very, very fast. And of course, now I'm reliant on this in-memory hash. So during crash recovery, if I would need to recreate this in-memory hash from scratch, or alternatively, I can also write it down somewhere. That's also possible. I believe in this code example, it is right. It doesn't store it. So right here, let's see the DB set. So we're setting the old content. Oh, we do store the hash here. So this does reload. Whenever we refresh, it reloads the hash. Okay, so very, very simple so far, right? It's just pointers and some in-memory hash to retrieve. Next slide. So some of the strengths we have, again, sequential writing is very, very fast, especially for these drives, because we are still appending to the file. It's still kind of like a lock, right? And there's some form of concurrency and crash recovery, because like when we write it to just that segment itself. So all the other segments are kind of safe, right? Yeah, and these segments are append-only. And there's very little defragmentation, again, because you're appending to a file. So some limitations is that your hash tables should fit into memory. Or you can also have different data structures to help handle this. But if you want to have almost instant hash to address, you need to keep this into the memory, right? And your range queries, let's say you are selecting a range of different keys, is not very efficient because all your data is, all your keys are not necessarily range searchable because you just store it into a hash table. So this sounds very simple, but it's actually very viable. This is actually what is being used in Bitcask, which is the default storage engine in React. And this is actually what's working under the hood for that. It has high performance read and write, provided that, again, all the keys fit into the RAM. So next, this is sorted string table and LSMTrees. When I wrote this, I think I misunderstood what the author was saying in his book, but I tried to give my best effort on trying to implement sorted string table and LSMTrees. So for my tree, so that's why there's a kind of caveat here. So for my tree, I'm just using a binary search tree, and this is a balance. I believe there is some balancing written there. Again, I wrote this code like 1 month ago, so I'm not sure if I remember everything. But yeah, so that's a lot of thing for the tree. So let's say when we insert anything, you can see it being represented in C1. So after a certain size, what happens is that we do kind of like what a merge sort does. Because you have everything that is in balance, so you have everything that is in a sorted order, it's very quick to merge. You just compare the first two values, and whatever is, whichever is smaller, you just put it together. And that's why it goes into the C0. So that's the sorted string table. So basically, the sorted string table is essentially just things where all the keys and values are sorted. All the keys are sorted, sorry. So you can change so in this code example, you can also change the different segmentation size. So just realized I was on the wrong code example. Yep, so over here we can change the segmentation size to maybe 4. Oh, okay, I need to open CodePen for that. And refresh, and then now when we add anything to the so I believe the next one should merge into the sorted string. Yep. So once I enter the next one, then it hits the maximum size that I want to have it in my insert table, in my insert tree, and then I store it straight into the memory as a sorted string. So when you can have multiple segments of sorted string this way, and you can merge it through again the merge sort strategy. So again, just comparing the first strings. So some learnings that I did from this, the LSM in LSMTrees mean there's a log structured merge, which happens periodically in a rolling fashion. So like what I did with the segmentation size, right? It rolls, it goes over to a certain size, and then it merges, goes to a certain size and merge. So you can have more than just 2 trees, but usually when we do the toy examples, it's C0 and C1, 2 trees. And then, so because C0 is stored in memory, right? The binary tree, that was very, very fast to insert. And it usually contains the constantly, frequently referenced nodes. And when you roll over, it gets a bit slower, but you can also maintain a different tree for quicker retrieval. Again, because everything is sorted, when you actually pull it from, when you actually pull the data, you do a logarithmic, it's a logarithmic search. So this also is good for searching within a range compared to the previous example where it's just a hash. Another thing, yeah, so I think I forgot what I wanted to say. Okay, next slide. So some improvements. There's this thing called a Bloom filter. It's a very space efficient probabilistic data structure. So sometimes one thing that's not very good about this form of searching is that you still require a logarithmic search, even though the key may not exist in your data storage. So what the Bloom filter does is that it kind of has this is this data structure that gives you a good enough reasonable assumption whether to even look into your trees or not. So you might even skip the entire tree if the Bloom filter just tells you this key is not your value, right? So it may contain false positive, so sometimes you might go into it even though you don't have the key, but it's better than having false negative where you don't look for the key despite it being in the structure. Yep. And then there are some strategies in merging compaction. Is size tiered, so small tables merge together into bigger tables, or you can also do level tiered where you have older tables and then you merge it together. Yeah, and also one of the other advantages is that you can actually merge these tables without first you can do it in memory. You can do it in place without actually taking additional memory. You can also do it while you are processing on some other thing. You can touch the untouched segments and merge them together. So the last big data structure that we learned in the book is B+Trees. So in B+Trees, this is quite similar to some binary trees that we are quite familiar with that we are familiar to code, but you can have so in this scenario, I have this constant order tree at the top. So what this means is that any point in time where I overflow each subtree, so each of this is basically a branch in the tree, right? So the 2 keys are references to the other tree. So for example, this is the root node. It has an ID of 1. And then depending on whether my new input is smaller or greater than this value, I will store it in either this side or this side, right? And this reference to ID 2, which is here, right? And so on and so forth. So this essentially still branches off into 2. This is binary. But what we can do here is, this is just for demonstration purposes, right? So when we enter something else, let's see, let's test. Oh, I do believe I need a key and value. Right, we can see that it got added, where was test? ID 4. Right, so it created a new leaf node here. I completely didn't plan it creating a leaf node, but here it is. And then since there's order 3, so if there's the next time I need to insert something within this range, it will actually create another node again, and this will split back into 2. So we can play around with this code example, and we can change the order to something a lot bigger. This one doesn't actually write to memory, unlike the other example. So this, because I couldn't figure out a way to do it. Oh, I think there's some syntax error. Oh, I think because the key exists. Nope, never mind. I'm full of nonsense. But basically you can choose how big you want each tree to be, and this guarantees that for each node, which can be a different part of the disk, it can be a different disk entirely, you will guarantee a certain size of at least the number of values that you can store inside. Oops. So some learnings that I've learned while doing this is that apparently B+Trees are more established than LSMTrees. They've been used more often historically, and yeah, so they store the tree as pages, right, of 2 kinds. So your leaf pages contains your actual data, whereas you have a lot of series of pointers representing which point to go. Again, this is kind of like it's logarithmic, but not to the base of 2. But you do have a logarithmic search, because again the tree is only certain level deep, right? And I believe in real world data, a lot of databases can actually just fit up to just 4 levels of trees, of leaves and pointers. And when you modify the data structure, they actually modify in place. So the way I realized when I was writing it is, when you build these trees, you're actually building it from the bottom up. So we first go down to where we want to insert, we put the value in, and then every time when we look at the parent again, we're like, oh, we might need to split and grow the parents to point to different places. Not sure if that analogy worked, but here we go. So some improvements that you can have is we can have some things like write ahead locks. So basically we have undo list. It's very difficult to remove things from such a complex data structure. So if you have a list of inserts and how you inserted it, it becomes a bit easier to remove it later on. You can also use a copy on write. So every time you write something, you'll copy the value into a new unused segment, and then your previous segment, you just keep it there until it reaches a certain number of writes. And you might want to add some thread locks to maintain the integrity during the updates, right? Because when you're writing, if you're writing halfway and you're manipulating the parents, if another search comes in during that time or another write comes in during that time, you will actually be stuck in a place where it may not exist anymore, or it might be a different branch. And the keys just needs to be abbreviated, because again, when you look at the key and value from here, right? This doesn't have to be the full value that you insert. It can be as long as it represents, when you manipulate it, it represents how it can be, how you can split into the different branches is good enough. So maybe the actual first 3 characters is good enough for certain cases. Yeah, so if you want it to be sequential, if you want to be able to read from leaf to leaf, you can arrange the page orders on the disk so that you can read it sequentially. So when you are reading through the disk, you don't have to jump back and forth between different segments. And there are some improvements where they use a sibling pointers of leaves. So when you want to read sequentially, you have a pointer at the end of the last leaf node, which points to the next part of the next leaf of the tree. But again, this is some overhead that you have to maintain when you write, because every time you create a new leaf, then you need to reference it in between. So some of the difference between the B-trees versus LSM trees is B-trees tend to have faster reads, while LSM trees tend to write faster. So pages are fixed size for B-trees, whereas for LSM trees, they do this sequential writing to the sorted string, right? And then for B-trees, your key only appears once, so it will, I believe it will rewrite, yeah, because it changes it in place. So you do have to keep at least a log if you want to undo any actions. And then LSM trees have compact data. Yeah, so B-trees, when you write, you only do a light locking. You only need to lock the segments that were being affected by adding a new leaf. Or if you're not adding a new leaf, you're just inserting a value, you don't have to lock anything except for that. So you can still access the rest of the tree. Whereas for LSM trees, you have, every time you compact your sorted string, you do that operation where you want to merge 2 segments together, it blocks your reads and writes for that. Basically for that whole chunk of data. So there are some other indexing structures that was also mentioned. So there's a full text search and fuzzy index. So some applications require searching for things that are similar. So this can be done by fuzzy indexes. Like Lucene allows for searching for words within a certain minimum edit distance. There's some code example here for minimum edit distance. Basically, is if you all did any CS background, you might have had to write this for one of your memoization? No, for one of your, I still remember the module name, CS3230. It's a nightmare. Anyway, yeah, so basically it's one of the dynamic programming, that's the word I was looking for. Dynamic programming common problems that you need to solve. You keep a table of your words, and then you calculate the edit cost and so on. So I don't think I will go deeply into the code example because I wrote this code 4 years ago when it's still fresh in my mind. So now that we've gone through some of the OLTP data structures, we can look into just a slight touch on the differences between OLTP versus OLAP, right? So again, transaction is for your businesses, your business logic, whereas your analytic OLAP, as you can tell from the name itself, is just the analytics. So usually, the read pattern for OLTP is small number of records, right? You usually only need to get data for one user, whereas for OLAP, you need to aggregate over a large number of records. You are usually analyzing over multiple different people, multiple different records. The write pattern is also different. So for OLTP, you cannot accurately predict when a user wants to add a certain key value or whatever when you want to retrieve later. There's just no way to do it. So I mean, there might be, but I don't know of a way to do it. So yeah, so you need, and your user wants your transactions to be fast, so your writes need to be relatively fast. Whereas for OLAP, you're doing analysis later. You can basically bulk import your data or have an event stream coming in to fill up your data. And you don't need to have you don't need to have current data that is available right now. You can just retrieve it and do your analysis over time. And your analysis is usually where your bottleneck is anyway. So for OLTP, again, primarily used by customers through web applications, again, business logic and OLAP analysis. So for the data-wise, OLTP only needs to represent what is your current state, what your users are currently using, right? But OLAP, you might want to have a historical record of everything that your user did, maybe for audit purposes, maybe for just analyze their usage. So the sizes also varies because of this, like from gigabytes to terabytes to petabytes. And yes, so for OLTP and OLAP, their bottleneck is usually different. So OLTP, because you need to write so often, you need to retrieve small portions of data so often, you probably jump in your disk a lot. So your seek time is usually your bottleneck. Whereas for OLAP, your bandwidth, like how much data are you getting from your disk at the time, that's your bottleneck. Okay, data warehousing. Generally, I think probably the MLEs in the room know better than me, but basically you want to have high availability and low latency. You want it to be available. You always want a lot of data to be available to analyze. And usually what you can do is you can copy the data from somewhere else. And yeah, you can optimize it for certain access patterns. The key indexing may not be important because you generally don't retrieve this data by a certain user, or you retrieve it in a group and then you do the analysis after that. So there are some structures that I will touch on. So there's a stars and snowflake schema. So for this one, you generally can have different dimensions for analysts to use for faster query time. Yeah, so the first one is star, the second one is snowflake. As you can see, this is more normalized, and then this you can't really see from the screen, but this has some repeated data. So the benefit of this is you actually just because you query the whole table together, you spend less time joining things together. But sometimes you can have data mismatch because of repetition, right? But it's also, again, it's fairly easy to set up. So you might want to do this as opposed to Snowflake, where you have you use less storage in total, but because of the no data redundancy, but this also means that your data tends to be more correct because you don't have repeated keys. So there's also a way you can have a column-oriented storage. So what happens is that you have, instead of storing things in rows, as you would in a normal database, you will store it in a whole column. All the values in the column are retrieved at the same time. And how this can kind of improve your retrieval is, okay, I already mentioned that, is that you retrieve the whole column at the same time. But how you maintain the values of the rows together is you must keep it in the same sorted order. So for column-oriented storage, you might have, so adjacent similar data. You can also compress things together if it's sorted in a good way. Like for example, you have all your users, you have, I was going to use gender, but I think gender is a bit more complex now. You only have certain months in a year where a person is born, and you can compact those together if that's the granularity you need. You don't have to keep it down to the last second, right? So you can compact some things together as long as you know they are sorted in a certain way and you know where the split lines for each different month is. In this case, it's just when they store it. So it's definitely different from the examples that I've shown, because the examples that I've shown are more optimized towards transactional. This is for analysis. So what you can have is you can still store it instead of storing it row by row, where you have a key and then multiple values, you actually store the whole column as one segment. But it needs to be, for every related segments, they need to be in the same sorted order. So if let's say you want to index meaning that your first column, right, will reference to the rest of your data. If you want to have multiple different indexes for different searching across different analyses, you need to actually copy the whole thing and then resort it and then do your compaction again. So it's a bit different. It's a completely different paradigm in how we would think to do a OLTP, like row storage. Yeah, so, okay. Yeah, I think I've talked about this already. So writing to column-oriented storage, again, just as I mentioned, is optimized for the reads, right? So when you write, you actually need to know, to know which is your important thing that you want to sort it by, and that's that helps you maintain which values are related to each other. Queries. Yep. Okay. I'll just move on. So again, or you can also have like materialized views. So maybe you only need certain related details together. Then you just keep a copy of those your transactional query, and then you store that. Whenever you need to analyze, you just take this view and pull it to your application. So there are also another way to kind of do the materialized view is you can have a multi-dimensional. It doesn't have to be a cube, but you can have multi-dimensional way of storing, of referencing the data. So in this way you can have slices of, you can slice depending on your column names, and then you get the related data in a already processed way. Yeah, but it does not have the flexibility as raw data because again, writing is very, very expensive. But when you query with certain pre-computed values based on how you want to slice your hypercube, that will make it faster. And that's the end of my talk. I forgot to put in a thank you page, but yeah, that's basically it. Thanks very much for listening. I hope it wasn't too boring.
Well, thank you, Ten, for our sharing. So now, is there anyone have any questions? Any questions from the floor? Let me check Slido.
Yes, Eugene?
Hold on. Let me pass you the mic so that it's recorded.
So do you plan to fork and write your own DB?
Do I? I think, I forgot to mention this, but like the reason why I chose to talk in GeekCamp was I feel like this is very useful knowledge, very interesting knowledge to know, but it may not be useful in your day-to-day job. So it's like kind of fitting to the theme of being a geek, right? I don't know when I'll ever use this. I read the whole book and I never use any of the knowledge, but nice to know. Whether I'll write my own, probably not. I know you did something with GitHub, using GitHub as databases before, right? Yeah, I think that's that is way more than I can ever write. I think someone else behind. Yeah.
Have you explored like memory store, like in-memory databases? Are they different from what you have just mentioned?
So I've used Redis. I wouldn't say I know it very well, but generally the thing about in-memory storage is that you usually have a almost instantaneous lookup for your key, and then you get your value instant. That's why it's so fast. Sometimes you can use in-memory storage in conjunction to your transactional storage, just because you want to retrieve faster. How they implement it, it could be as simple as a hash, or it could be more complicated. It really depends. The problem with in-memory storage is when you have part of the, let's say you have multiple in-memory storage, like multiple Redis, and then you have one that's down. When you get it back up again, you need to rebuild it, and that costs some time. So you will also need to fall back to the transactional database in those scenarios. Yeah, I hope that answers the question.
I think I have another question from there, right?
Oh yeah, thank you for your talk. I think it's a very good breakdown of like OLTP and OLAP. Could you share a bit about how databases manage like replication? For example, in a like high availability scenario or distributed database scenario, how would multiple nodes handle like fault tolerance?
There is a chapter in the book about that. I'm not sure whether I can remember it. There are a few multiple strategies. Of course, duplication is always one of the ways. But with duplication, that means you need to write more times, right? But that's the most straightforward way to implement. In certain cases, like you can also look back to how we do disk duplication, like your rate 4, 5, I don't know, but basically you kind of have a parity thing to kind of make sure if you do lose a data, if you do lose any of your duplication, you still have the thing that can be rebuilt. So for multiple different, and also for duplication, generally you will have a leader follower kind of structure, right? So in those scenarios, generally the difficult part is actually choosing the leader. Not a lot of there's very complicated algorithms in finding out which is the leader, and when the leader dies, what happens? Do you choose? Did the leader elect another leader before he died, or are you going to compute and see who's the new most eligible leader? So those are more than half an hour talk in each of yourself, but it is, yeah. I hope I can cover a little bit of these concepts.
Okay. Yeah, thank you.
So any more questions from the ground? Actually, I have one question. How long does it take for you to read the book? And how long does it take for you to implement all this?
Okay, so it took me, effectively 13 weeks, but it was over a longer period of time. So every chapter 1 week, there's 13 chapters altogether. We did skip a few weeks because we were like, oh, we need to ship this other, we need to actually do work. So we need to delay the speech by need to delay the talk by another week. And yeah, and then luckily there was a period of time when I was reading this book and I had to do reservice where I spent a lot of time doing nothing in camp. So I got the book on PDF and I read it. How long it took to write the code example? I believe I would say about 10 hours total. So a lot of these things, I'm really rusty with my data structure, so I built the binary tree, I built the B tree from scratch.
But that's still very fast, right? I think. I feel.
First two were very fast, half an hour.
I think we have another question from Slido. So what would be a good database structure for an application that sits somewhat in between OLTP and OLAP? So for OLAP, should we also consider ad hoc versus big ones?
I think this question, the person who asked this question probably has more knowledge about databases than me. Again, I've only started doing full stack in a year ago.
Okay, so yeah, okay.
Sorry, I can't answer that question.
Yeah. Okay, so any more other questions? Anyone want to ask anything?
Do you have any tip on how we can somehow conquer or solve the problem with the trade-off? Like when adding indexes, right? So the read gets faster, but then the write gets slower. So any tips on that?
Generally, again, like you mentioned, it's a trade-off, right? There's just always going to be extra costs. So a few ways you can do is when you have when you're not reading certain things, you can compact your data structures so you can be faster. If you're writing to a very long hash, you might have some collisions that will take a bit of extra time. So occasionally you might want to do some housekeeping and all that. Usually this is done invisibly to the application developer. So as a user of a database, there's probably some settings to change. It's not as complicated as you have to write your own way of managing. So again, like the rolling your own crypto, right? You probably don't want to roll your own DB. Probably not. Yeah, I hope that answers.